Hello everyone. Today we will study the method of Lagrange multipliers for the constraint extremum problem of multivariate functions. In last section, we discussed the free extremum problem, such as finding the minimum value of the following function, where xy is only restricted in the domain D, and the variables xy have no other constraints. What's more, there is another type of extremum problem, constraint extremum problem, such as finding the minimum value of the following function. Subject to some constraint phi xy equaling to 0. Many of the problems in real world, especially those in economics, are of the net type. For example, a manufacturer may wish maximize profits, but is likely to be constrained by the amount of raw material available, the size of its labor force, and so on. Next, we will solve a specific problem to get the idea of solving general constraint extremum problems. Suppose the sum of the length, width, and height of a rectangle is 18. What values do they take respectively such that the volume of the rectangle is largest? Solution: assume the length, width, the height are x, y, z respectively. Then the sum of x, y, z is 18. The volume V of the rectangle is x, y, z. In this problem, the independent variables x, y, z are not only restricted by the domain, that is, x, y, z must be larger than 0, but also constrained by the equation x plus y plus z equals 18. This is a constraint extremum problem. In order to solve it, we can derive z equals 18 minus x minus y from the constraints, and substituting into the volume V to obtain that V equals this term. The domain of this new function is D. X, y are larger than 0, and x plus y is less or equal to 18. So we turn the constraint extremum problem into free extremum problem. Let the two partials of V be 0. We obtain the stationary point 6, 6. Since the volume V has the only stationary point in the domain D, and V must have maximum value, then when x, y, and z are all equal to 6, V has the maximum, and the maximum value is 216. The above example can be considered as finding the extreme value of V subject to the condition x plus y plus z equals 18, where this function V is called objective function, and this function is called the constraint. Hence, the example is called a constraint extremum problem. In some cases, the constraint extremum problems can be transformed into the free constraint extremum problems through substituting the constraint into the objective function. But in general, it is difficult or impossible to do so. The following we introduce the general solution to the constraint extremum problem, Lagrange's method. Now we find the necessary conditions for the objective function z equals fxy subject to the constraint phi xy equals 0 to obtain the extremum value. If the function fxy has the extremum value at x point, y point, then phi x point, y point equals 0. By the constraints phi xy equals 0, if y is an implicit function of variable x, that is, the composite objective function f(x, y(x) has the extreme value at x points. By the necessary conditions for obtaining the extreme value of univariate differentiable function, we have dz dt equals 0. Note that y equals yx is implicitly defined by phi xy equaling to 0. So the derivative dy dx is this term. Substituting into equation 4 to obtain the equation 5. The equations 3 and 5 are the necessary conditions of obtaining the extremum value for the function 1 under the constraint 2. Let lambda be this term. Then the above necessary conditions can be turned into the following equations 6. The left of the first two equations of this equation are the two first-order partial derivatives of the function Lxy. And the left of the third equation of 6 is exactly the partial derivative of L respect to lambda. The function Lxy equaling to fxy plus lambda phi xy is called Lagrange function. The corresponding lambda is called a Lagrange multiplier. Using the vector p, we summarize the above method as the following theorem. To maximize or minimize fp subject to the constraints gp equals 0, solve the system of equations del fp equals lambda gp and gp equals 0 vector for p and lambda. Each such point p is a critical point for the constraint extremum problem, and the corresponding lambda is called Lagrange multiplier. Example 1. Find the shortest distance from point P to the surface z equals x squared plus y squared. Solution. Let Q, x, y, z is a point on the surface. The distance between P and Q is as follows. To simplify the calculation, let fxyz be equal to d squared, that is, the following term. The problem is to find the minimum for the function fxyz subject to the following constraints. Let Lxyz be this function, and the partials of L with respect to x, y, z, and lambda are as follows. By equation 1 and 2 and 3, we have the relationship between the independent variables x, y, z and the multiplier lambda as follows. Then x equals y and y equals 1 over 2z. Substituting this term into equation 4 to obtain the following values of x, y, and z. So the only stationary point is P. Since the problem exists the minimum value really, then at the point P, the distance d has the minimum value as follows. Example 2. We have the tangent plane of this and poset in the first constant such that the volume of the tetrahedron is minimum, where the tetrahedron is surrounded by the tangent plane and the three coordinate planes. Try to find the coordinates of the tangent point. Solution. Let P is a point of the ellipsoid. Fxyz is this function. Then the three partials of capital F are as follows. Then the tangent plane which passes through the point P is this one. Simplify it as this term. So in each of the three axes, the intercepts of the tangent plane are the three terms below. So the volume V of the tetrahedron is the following expression. Subject to the constraint, this term. So we get a constraint x-term problem. Let u be equal to the function, and let Lagrange function be as follows. Let the partials of L be 0. We have the following equations. That is, this system of equations solving for x0, y0, and z0, we get the only point P, which is the tangent point, and the minimum value is this one. Similar to a function of a single variable, we can find extreme to obtain minimum and maximum of the function over a closed and bounded set. Here is a general method of finding the maximum or minimum. First, find all possible extreme points of the function of the interior of D. Second, find the points along the boundary that give the maximum or minimum. Finally, evaluate the function value at obtained points to find maximum and minimum over D. Example 3. Find the minimum and maximum for the function over the round. Solution. We first find the possible extreme points of the function z equals x squared plus y squared in the interior of the round. Let the two partials of z be 0. We get the stationary point 0, 0. Second, find the minimum or maximum for the function z along the boundary of the round. The Lagrange function is this one. Then we have the following system of equations. X and y have the values. Comparing the three values on the round to obtain the maximum value is 25 and minimum value is 0. Remarks: how to determine the points obtained is extreme point. In the practical problems, we can determine according to the nature of the problem. For non-practical problems, we will not discuss further here. At last, it is easy to extend the method of Lagrange multipliers to the cases of more than 2 variables and several constraints. Now, let's make a summary of this section. We learned the Lagrange method of constraint x-term problem. The basic idea of this method is to transform constraint x-term problem into free x-term problem. In order to find the possible extreme points of fxy subject to the constraints phi xy equaling to 0, we assume a Lagrange function. Then let the partials of L with respect to x, y, and lambda to obtain the system of equations. Finally, find x, y, where xy is the coordinates of the possible extreme points. That's all today. Thank you.